Hi! In this video we will try to construct a model in order to determine the probability that the next earthquake in Reykjanes, Iceland is in a certain range of magnitudes. We will use a dataset of 365 earthquakes in Reykjanes of magnitude at least 1 to achieve this. To do this, we consider the random variable m, which is the magnitude of the next earthquake in Reykjanes. We learned that we may express the probability that this magnitude is higher than the value a and lower than the value b in terms of the distribution function or probability density function, as you can see on the slide. Thus, we will aim to determine the probability density function. By now we have seen two continuous distributions, namely the uniform and the normal distribution. It seems unreasonable to assume that magnitudes of earthquakes are uniformly distributed. Indeed, it seems high magnitudes happen less often than low magnitudes. So let's consider the normal distribution. To determine the probability density function fully, we need to find out the relevant parameters mu and sigma squared. Due to the symmetry of the normal distribution, we see, as indicated on the slide, that the probability of being lower than mu is a half. So it seems reasonable to use the middle value of our dataset as mu. In other words, the magnitude in our dataset such that half of the magnitudes in our dataset are lower and half of them are higher. You will see in class that this is the so-called empirical median. And our choice here means we consider a model whose median matches the empirical median. Notice how we used our data to estimate an unknown parameter of our model distribution. Looking at our dataset, this means we obtain an estimate mu hat for mu of 1.3. Let's use a similar technique to determine a good value for sigma squared. We saw in class that for a normal distribution, the probability to end up within one standard deviation of mu is approximately 68%. So it seems reasonable to choose sigma such that approximately 68% of the dataset is within that distance of mu hat, which was 1.3. Looking at our dataset, this means we obtain an estimate sigma hat for sigma of 0.31, and thus an estimate sigma hat squared for sigma squared of 0.0961. Plugging these parameters in the formulas for the probability density function of the normal distribution, we find the graphs for the probability density function and the cumulative distribution function that you can see on the slide. Based on this model, we would for instance predict a probability of 0.012 that the next earthquake has a magnitude between 2 and 3. Before communicating this prediction to the fine residents of Iceland, however, let's hold up a minute and critique our model. Let's use our dataset to check whether our model makes any sense. We already know that our model makes perfect sense if we consider the median and the middle 68%. In the sense that the median of the model distribution matches the median of our dataset. And the probability of the random variable in our model being between 0.99 and 1.61 matches the proportion of data points between those values. Indeed, this is how we constructed the model. So what else can we do to check whether this model is a good fit for our data? We saw in class that the normalized histogram is a good estimator for the probability density function, and the empirical cumulative distribution function is a good estimator for the cumulative distribution function. So a way to check the goodness of fit of our model is to see if the normalized histogram and the empirical distribution function for our dataset, both shown on the slide, match with the probability density function and the distribution function of our model. So let's plot these in the same picture. Here you can see the result. Clearly, they don't match well at all. This is most obvious when looking at the probability density function, in contrast with the normalized histogram. In fact, this contrast makes clear that we will not be very successful matching the probability density function of any normal distribution to the normalized histogram. Indeed, our method above does mimic how we determine parameters of a model distribution, but it was doomed from the start since the data clearly does not come from a normal distribution at all. To be clear, the problem is not our estimates of mu and sigma squared. Those are fine. The problem is that we started with the wrong kind of possible model distribution. So we will need a much larger repertoire of known distributions in order to accurately model data in practice. Luckily, we'll get to know many more distributions in the future. Goodbye.